Last time we were talking about the D latches, and then we introduced the D flip-flop. Now, another flip-flop I want to talk about, and it is very, very important, is the JK flip-flop. So let's draw it. I'm going to draw the schematic first. So, well, basically, a JK flip-flop is this: J, Q, Q naught, K, and here goes the clock. This is J, this is K, then we have the output Q and Q naught, and this is the J, K, flip, flop here. And again, this is one of the most important flip-flop. So again, flip-flop basically means that we have this edge sensitive property of it. So when we have been talking about something like, latches, like this one, like the D latch or the SL latch and so on, that basically meant that it was not edge sensitive. We might have something like an enable pin, like in the D latch, but as long as the enable pin was high, we would, change the output. But with a JK flip-flop, the output is only gonna be valid when this clock is, when the clock, we can basically sample the J and the K value on the clock edge. So we're basically going to have a truth table for this JK flip-flop, and I'm going to draw it right now. The truth table here, in this case, if we say J, K, Q, Q plus, we set J to 0 and K to 0, then Q was going to be 0. If we set J to 0 and K to 0, it will be Q as 1, Q plus going to be 1. If we set J to 0, K to 1, Q 0, and Q plus 0. If we set J to 0, K to 1, we have 1, 0. If we set J to 1 and K to 0, then we have 0, 1. If we set J to 1, K to 0, that we have 1, 1. And we set J to 1 and K to 1, then we have 0, 1. And if we set J to 1, K to 1, we have 1, 0. And in this period, in those value here, we have the, if you remember the previous video when I've been talking about hold time, setup time, hold time, and delay time. In this case, we're going to have hold time, in which is going to hold the values, the reset time, which is going to reset, the set time, which is going to set, and toggle time, in which it basically toggles. And again, this truth table not showing the clock, it's just saying, just showing what's the value of J and K on the clock edge. So basically on when if you have here the clock, when the clock is here on the clock edge, right? So again, this is basically what is showing. It's kind of similar to the RS flip-flop, And so if j and k are 0, the output is just gonna stay the same. If k goes to 1, then the output always goes to 0. So k, we can basically think about it as sort of reset. And in the same way, j is kind of a set pin, because if j is 1, the output always goes to 1. But if j and k are both 1, then the output toggles. So if it's 0, it becomes 1. If it's 1, it becomes 0. So this is basically the main difference between the JK and the RS. So we have this property that if both inputs are 1, the output toggles between the two values. So yeah. So this is basically the main difference between a NES-R latch and a JK. So if we connect those two together, so the J and the K, we can basically create another flip-flop, which is the toggle flip-flop. So let me just redraw this just to make things a little bit more clear. I can actually say, okay, if I redraw this like this, and I put this one as J, this one as K, Q, Q naught, and then we have this. What I'm going to have in this case will be, like connecting the J and the K together, okay, like this. And then here, still having the clock. So this one is basically exactly like showing something else, which is the flip-flop toggle, which I can simplify like this. We have our element with a T, Q, Q naught, and here we have the clock, so the output, and the complemented output here. So the toggle flip-flop is actually kind of useful to divide clocks or other stuff. So for instance, let's suppose that you have a clock which is like, I don't know, like this. So if we have a toggle flip-flop, if J and K are both 1, so basically here we have 1, and I basically get this one connected here. Basically what happens is that Q is kind of toggling. So it goes from here, here, and here. If the initial state is 0, it goes to 1, and then all the way to 0, and then all the way to 1. So you can basically see as that you can use this as a frequency divider, because the input has this period here. We're gonna call this, I don't know, like T or something. But you can see the output here because it's toggling on every rising edge. And the period here is basically twice. I can say 2T. So you can basically also bunch more of them together if you wanna, divide by, not just 2, but something more. So yeah, the flip-flop toggle is actually very important, and it comes from connecting together JK flip-flop, and JK flip-flop is basically this, as I basically went through the table, and I just stopped, drawing circuits within the elements, because I think that this way of representing them, it just, the right abstraction level that I'm going to use, because, it just makes much more sense to look at it like this. So yeah, so basically those are the property of a JK flip-flop. You can basically think about this J as a set and a K as a reset. The only property, special property that it has, compared to what we have seen before, is that if you set both J and K, so basically set and reset to 1, then the output is going to toggle. And if we connect those two together, we get a flip-flop toggle. I'm going to say this, I'm going to label this, so flip-flop toggle. It's also called, sometimes it's also called T flip-flop. It just, it depends. Some books call it T flip-flop and other flip-flop toggle, but honestly, just, it's just toggling, so it's the toggle. So yeah, I think we're covered enough here for this video, so this is gonna be pretty much it. Stay tuned for the next episode.